Hey, what's up?
Hey.
Can you hear me okay?
Yes, I can.
Okay, just making sure. I just got everything set back up. Casey and I went to visit my brother in New York this weekend, so um,
Oh,
getting
yeah, that's
everything
what you were saying.
put
I
back
hope it went
together.
well.
Yeah, it was a ton of fun. I'm just my feet are so tired from walking so much. Um, but yeah, it was a ton of fun. Um, how was your weekend? How doing all this prep end up going?
It's been okay. It's been busy. I've been up for 30 hours now.
Oh, that sucks. I hate that feeling. I do that a lot. So, definitely understand. But yeah, that's not a fun feeling. Let me know if you need to cut it short or anything, or if you're ready, if you need to go to sleep. Like, I don't want to waste your time
No,
if you're tired.
no, it's okay. I'm good.
Okay, cool. All right. But if you change your mind, definitely let me
Okay.
know because I know the feeling all too well. Anyway, so do you have any questions to get started here?
Um,
Any questions on any of the stuff you read or anything else or anything
I'm gonna
period?
be completely honest. My brain's fried right now. I do remember I did read through all the chapters. I don't know how
Hmm.
much I recall.
That's okay.
I do want to go over like just the physics stuff, the thermodynamics and fluid stuff because that was all kind of new to me.
Right. Okay.
I didn't have any specific questions about it. It's just more of like fully understanding what everything means.
Okay.
I know that's really broad and doesn't
Oh
narrow
no, yeah,
anything
yeah.
down.
No, you're totally fine. We can definitely do that. Also the chemistry, so the physics stuff, I'll try to walk you through some of this physics stuff here. Um, it's kind of difficult to do a thorough job without like specific questions just because
Mhm.
there's so much of it. And also I definitely want to spend some time talking about some of the chemistry concepts because the specifically like the equilibrium chapter here in chemistry in Gen Chem is super important. It's probably like one of the most important chapters in this book. uh just just in terms of like how likely it is to be tested on the MCAT, because
Okay.
all the other concepts kind of relate to it really well. Um, Also, as you can see, the thermodynamics chapter in physics and the thermochemistry chapter in Gen Chem, there's
Related.
a reason. Yeah, there's a
Yeah.
reason I put those together. There's a ton of redundancy there. I don't know why they don't just make it one big thermodynamics chapter and pick one to put it in, but whatever. Um, so yeah, we can start out by doing some of that. I've got some pre-made images and stuff that I think will help us out a lot too. Let me go ahead and share my screen to
Okay,
get
thank you
started.
so much.
Oh yeah, no problem.
Oh,
Um,
and then one thing I noticed I don't
uh-huh.
have the like um the the chart that says like what to work on and what not to work on in my folder.
What is that?
The
Which
chart
chart?
that says like you know how it says like day 2 physics 3 to 4 general chemistry like what
Oh,
you've
that's not
copied.
in there.
Yeah, it's not in
Oh,
there.
I'm sorry. Okay, I'll make sure that that gets put in there. I'm gonna make a note right here at the top.
Okay.
Just that way because if I try to do it while we're on the call here, you'll just have to watch me do stuff for a little
No
bit, and that's
worries.
a
I
waste of
was
your
like
time. But
looking through it because I was like I know I've read through all these just can't remember which chapters it was.
I'm just calling it syllabus for myself here. Put the syllabus. There we go. Yeah, I'll see that at the very top once I go back and start editing things. Also, I changed my default font on this, like whenever I'm doing stuff, to this Comic Sans thing, which I know Comic Sans is like the classical like font you're not supposed to use for anything professional. But it is also really good for people with dyslexia to read faster. And turns out like a surprising number of people who have dyslexia. Also I do, I know. So let me know if it's annoying to you or
Oh
whatever.
no, you're good.
I also did it because I'm making a bunch of these videos uh for this company, and we're gonna use some of the images that I made for these videos here today. Um, but let's see, where is this thing? Oh, there it was. I just saw it. Okay, cool. So like we talked about this graph already some. the Gibbs free energy and
Yeah.
all of that stuff graph. But this will be really important today, and a lot of the stuff we talk about, because it's kind of everything kind of goes back to this graph, especially on stuff today. So right, because you read through the thermodynamic stuff, and that generally speaking, like most important equation in a lot of this thermodynamic stuff that we'll cover is the delta G equals delta H minus T delta S equation.
Mm.
And I think we did talk about this equation some the other day, right?
Yes, we did.
Okay, I just wanted to make sure. Okay, so what does this walk me through really quickly, like what this equation is sort of saying? What is delta H? What is delta S? All that stuff.
Okay. T is temperature. Delta S
Mhm.
is the change in enthalpy. Yeah, one that starts with an E.
All
Shouldn't
right.
mix those up.
Yeah. So delta S is entropy.
Entropy. Yeah. Okay. And then delta H is change in heat. Correct.
Yeah, or enthalpy. So it's
Enthalpy.
yeah, which is it's really similar to heat. Um, and so it turns out delta S, or entropy, is just a measure of like chaos or disorder or randomization in a system, however you want to think about that. Remember, we discussed how it's like if you have a bunch of particles in a closed space,
Yeah.
then you can have more possible configurations. And so delta S is just like how many total possible configurations, and how did that number of possible configurations change over the course of whatever process we're looking at.
Yeah.
Right. And whereas delta H is like the energy released or absorbed by bond formation or bond breaking, depending
Mm.
on what it is that happened there. And so those two are juxtaposed against each other in this equation. So what is temperature? What's the definition of temperature that they gave you in the book, or what? Like, how would you think about temperature?
If I remember, the book described it as um, like the energy in the molecules.
Okay. Yeah. So specifically, it's the average kinetic energy of the molecules in the system. So meaning that, like, obviously, like each. So what is kinetic energy even?
So kinetic energy is like movement. It's like molecules moving. It's like, you have your potential energy, which is like, I hate using the same word, but the energy the things could have, the
Mhm.
molecules could have, and then kinetic energy is when that potential energy gets transformed into that action or that work.
Yeah, it's tough to describe,
Yeah.
isn't it? Yeah, it's like, yeah, so everything's gonna have like some total energy, right? And
Mm,
that total energy is gonna be a combination of how much potential energy it has and how much kinetic energy it has.
mm,
And you're right that potential energy can be transformed into kinetic energy. It's no longer potential at that point; it's being active, right? And so,
yeah.
like, how much kinetic energy something has is going to be directly proportionate to the square of its velocity moving through space. So, because kinetic energy, there's an equation that you'll need to know eventually. I think it was in the last times reading, actually, that kinetic energy of any particle is just 1/2 times the mass of that particle times
Times
the
the velocity
velocity
squared.
squared.
And
Right.
then
Yeah, exactly.
you have your I don't know the name for it, but you have your potential energy, like U naught plus K naught is equal to U final plus K final.
Uh yeah, so that is the conservation of energy
Yeah.
equation, right? So, yeah, because the U is potential energy. Sometimes you see it written as PE, sometimes you just see it written as U, right? Um,
Mm,
but yeah, either way, so we could just say that's potential energy, and that is, like you said, or that's equal to mass times the
gravity,
acceleration due to gravity
and
times
then the height.
something. Right. Right. Yeah, exactly. Okay. So that's a good analogy for thinking about the energy in a system, or like the energy of an object or something, if you're thinking about like a ball and a hill,
Mm,
for instance. So like, let's say this is from here to here, and let's say this goes to there. That was a terrible drawing, but it doesn't matter. So from here to here, we'll just say that this is like 10 meters, right? So then this valley down here would be 0 meters, and let's say that this is like 3 meters high, right?
Mm.
Let's say that this ball weighs, this is a 1 kilogram ball. Okay, so what's the total energy of this ball, assuming no friction or air resistance or anything? What's the total energy of this ball at the very top?
100.
100? Yeah, because you've got 1 kilogram, right? So times 10 meters per second squared times 10 meters. Yeah, exactly. It's 100. Okay, so your total energy is 100 there. What about if we then, like, the ball starts to roll down this hill? What about whenever it gets to this point right here? What's the total energy of the ball?
100, but it's kinetic energy.
Okay, yeah, exactly.
And that's
it's
assuming
still
there's
100.
no friction or work done.
Right. Yeah, exactly. Okay, so how fast is it going then at that point?
It is going. So if kinetic energy, sorry.
Oh no, you're good. It's not a super easy question. So yeah.
Isn't it just 100 squared?
Yeah, it's gonna be like, so because your potential energy up here, you just had potential energy up here was equal to, right? You said 100 joules.
100.
So kinetic energy down here is going to be equal to 100 also, which is, you said that, right? And that's going to be equal to 1/2 times mass times velocity of the thing squared. So since mass is 1, right, then we can move that over to the other side, move that and the 1/2 over to the other side. So it's 200 is equal to the velocity squared.
Yeah.
Right. So then your velocity at that point, I'm running out of space here. Let's just say that 200 is equal to your velocity squared. So that tells you that your velocity is equal to radical 200, which, is going to be like radical 2 times 10 or something like that, or 10 times radical 2.
Real quick, how can you relate the proportion that kinetic energy is proportional to the square root of velocity here? Is there a relation here?
Could you restate that? I'm not sure exactly what you're asking.
Because earlier you had said the kinetic energy in the system is proportional to the square root of its velocity.
I said the square of its velocity.
The square. Okay, there we go.
Yeah, like it's yeah.
Mishap of me writing.
Yeah,
okay,
that's yeah. Go ahead.
That fixes my question.
Okay, yeah. And that's kind of my fault a little bit. Like saying the square of something is different. Is people by default think square root rather than the square. But yeah, kinetic energy. I could also say that, like, the square root of, I don't know, the square root of kinetic energy is proportionate to velocity. That that would also work. But kinetic energy is proportionate to I was basically just stating this equation.
Yeah.
Whenever
Okay.
I said that. Yeah.
Okay. Cool. Thank you.
Oh yeah, no problem. Okay, so yeah, so at that point the velocity is 2 times, so it'd be like v is equal to 10 times radical 2, right? So that tells you that velocity is like 14, right, at that spot, because radical 2 is just gonna be really helpful for you to just know off the top of your head that radical 2 is 1.41 ish.
Okay.
Yeah. Which is something I'm sure you've seen before. But okay, so then what if I ask you how fast is the ball going then once it gets over to this point at 3 meters?
All right. You just have to do the equation, right?
Mm-hmm.
Then that's 100 minus 1/2 10 100 squared. No, hold on 1 second.
Okay.
Looking for velocity. So then that'd be 100 minus what is it? 3. So that's 3 times 10, 30. 30 times 10 is that doesn't make sense. Hold on. Wait, no. Let me start over. Sorry.
Okay. No, you're good. You're good. No need to try to rush through anything. Like it's just you and me here. So
Okay.
yeah, you're fine.
So initially the ball only has potential energy, so that's mgh, which is 100 joules. And then at 3 meters, it'll have kinetic and potential energy.
Mm-hmm.
And then we're gonna solve for velocity, which will be oh, that's what I did. I put a 10 instead of a 1 in my head.
Okay.
And then multiply all that by 2. So then that's 140. Right, and then mass is 1. Then you take the square root of 140.
Square root of 140.
Yeah.
Which is going to be, I'm trying to think. Yeah, I should know that. Oh, well, whatever. I don't know that. I guess it'd be like 11.7-ish or 11.8. So the
11.8, yeah.
How'd you get there exactly? I'm not
I
saying
use the conservation of energy law, and
Okay.
I set up the equation as U naught plus K naught is equal to UF plus KF. And then
Okay.
I reasoned out that the ball started with only potential energy, and then at the end it's ending with both potential and kinetic energy, and then I solved for velocity.
Okay, yeah. So basically you had this 100 and then you said mgh at a height of 3, mgh turns into 30, right?
Yes.
And so then you get 70 is equal to 1/2 mv squared. Is that what you did? Okay.
Yes.
All right, cool. I just want to make sure. Yeah. That's exactly right. All right. So that works extremely well, right? And so in conservation of energy is like your fallback for all physics problems on this test. If you see a physics problem and you're not sure how to do it, just get to conservation of energy and it gets you there like 99% of the time. It's really great. However, conservation of energy gets tricky whenever we start thinking about fluid dynamic issues, right? And so this is kind of a way of combining the thermodynamic stuff and the fluid dynamic stuff that you're just looking at. So, all right. So what if you have a system set up now? This is going to be almost an identical problem, but now instead of a ball on a hill, we've got a fluid situation where let's say you've got like a water tower or something here. Okay, this is your big water tower, and let's just say that it's just like a giant bucket of water, whatever. All right, so it's 5 meters tall. All right, and then it goes into this pipe. The pipe goes under the ground, and we'll say that the pipe runs under the ground for a really long ways, like 300 meters or something. Okay, and then the pipe goes up above the ground and comes out, let's just say, in like a singular faucet in your house. All right, and that singular faucet, so total, this whole thing is, let's say, 10 meters tall, and this whole thing is, let's say, 4 meters tall. All right. So the fluid level is all the way up here at the top, right? So you've got fluid in this, you got water going through this thing, right? So the question is going to be, how fast is the water flowing when it exits your faucet, which has a diameter? Oh, and this is also 5 meters. Sorry about that. And this faucet has a diameter of, let's say, 1 centimeter. So this is 0.01 meters. Go ahead and do the conversion for you because that's a pain in the ass whenever. But just keep in mind they're likely to tell you 1 centimeter diameter or something like that.
Okay.
All right. So yeah. So how fast? The question here will just be, how fast is the water flowing? Or how fast is the water shooting of your faucet? How do you go about solving this? Because this gets a little bit more complicated.
My initial thought is to use or try to use Poisler's law, but we don't have the pressure gradient here, so I can't use that. Um,
Okay. So what if I tell you that's a really good point. I guess maybe I should have mentioned this is open top. So at this point, you do have the pressure gradient because you can assume atmospheric pressure on both
okay,
sides.
pressure. Okay, and then do I have uh even with that though, I still don't have the weird end looking thing, which is the um what is the eta, the viscosity of the fluid.
Oh, gotcha. Yeah. So you're talking about the row sign, or
Yeah,
you mean or viscosity?
yeah,
I don't think you
eta.
need it.
It looks like an N.
I know what you're talking about.
Yeah,
So, and I was thinking you were talking about a different equation. So you're talking about the Q equals
pi r to the fourth power delta
yeah,
p.
yeah, this is a complicated equation. Pi r to the 4.
P over 8 eta L.
Mhm. Yeah, that thing is hard to draw. Okay. So, yeah. And what is that equation for? What's that equation solving for?
That equation's solving for the flow rate,
Right. Yeah,
volume
exactly.
flowing per time. Oh, I guess that's not what we're looking for here.
Right. Yeah, yeah.
Okay, not what we're looking for.
But that's cool that you knew that equation that was available to you. I'm trying to
Okay,
think if you could use that, but without knowing the viscosity, you're right. It would be kind of impossible to
yeah.
use that. So, yeah, yeah, yeah. But good thinking.
Um, you could kind of think of this as like conservation of energy, but like
Mhm.
subtract work because there's work being done by the water. Isn't that right? Or like the water flowing through?
Um, so why would you? So you'd subtract work in what way? Sorry, I'm about to sneeze.
Okay. Um,
Sorry
bless you.
about that. I just didn't want to sneeze right into the microphone. um, so, yeah. So the water, I guess. I'm trying to think whether the water is actually doing work here. It's kind of a weird question. Uh, I don't think the water's really doing work on anything here because the system itself isn't like expanding or contracting in any real way. So the water is flowing, but if anything, maybe you could say like the force of gravity is doing work on the water, like
Because
moving it
yeah,
downward because you got
because it would
water above.
doesn't it move it downward and then when it goes back up, gravity's doing work on it as it's trying to flow back up.
Yeah, technically, like it'd be slowing it down as it moves back up and goes out. But you don't
Yeah.
need to subtract the work that gravity's doing because this is like a continuous process. So
Okay.
think about how this is literally identical to the picture that I drew up here.
Yeah.
See what I'm saying? Other than the fact that I said 4 meters instead of 3 meters, but whatever, we can leave it. 4 is fine. But like it's an identical situation except for the fact that if you do try to use conservation of energy, the mgh1 plus 1/2 mv1 squared
Mm.
equals mgh2, because this is really conservation of energy right here, written out formally, mv2 squared. If you try to
Mm.
use that, you run into the issue that you can't really say like what the mass of that water is or what the height of that water is in any of these scenarios, right?
Yeah.
So that's really why this would be like impossible to use, because you can't really say like what the mass of the water is, what the height of the water is. It's really difficult because what makes that difficult?
Because the
Like,
water's flowing.
yeah, because the water it's a flowing situation. It's like a continuous water is a continuous thing. It's not like a finite body that's rolling down this hill, right?
Yeah.
So what you need is a conservation of energy for fluids specifically.
Okay.
All right. Do you have anything available to you that is like that?
I don't remember if I'm being
Okay. All
honest.
right. Yeah. No. You're good. You're good. This is like the hardest. This is, fluid dynamics chapter is one of the hardest things in my opinion, personally. And this is not just me. Like everybody kind of agrees on this. So, um, the way that you can. So if you think about like what in okay, so how can you relate just like a finite confined mass to a flowing something that's continuous like a fluid? Well, when we think about the mass of this ball, we're also thinking about like we know how much volume the ball takes up, but we don't really know how much. We can't really say how much volume the water takes up. I mean, we can, but then we'd have to be confining it to a segment of that
Mm,
thing, right? But we can say how much mass there is of water per given amount of volume,
okay.
right? So whenever you're talking about fluids, you can still use this exact form of conservation of energy, but you just have to think about mass per volume rather than just mass because you haven't defined your volume yet. Does that make
Okay.
sense?
Yeah.
Okay. So if you divide both sides of this equation, and if you divide both sides of this equation by volume, then what you end up with instead of mass, so you've got mass times GH1, right? But if you've divided that whole thing by volume, then that ends up being density times G times H1, right? Because mass divided by
Yeah.
volume is density.
Yeah.
Similarly, if you divide 1/2 mv squared by volume, then you end up with 1/2 density velocity squared, right?
Mm,
So that would be like that side of the equation. And then you can do the same thing with the other side of the equation. And so what you ultimately end up with there is you've got density times G times H1 plus 1/2 density times velocity squared. And so it's the same exact equation. You've just replaced mass with density at every point
okay.
here. And so this is, oops, I just put mass in it right after I said to replace it. So this is what we call Bernoulli's law, this equation.
Okay.
And I think it's the last equation. Like if you look at the equations to remember page
Mm,
in the physics book, I think it's the last equation on that equations to remember page. Um, but I haven't accounted for one last variable that's on each side, right? You've got the P1 and P2 thing on each side of that equation as well. So what does that P1 and P2 refer to?
um, does it refer to pressure?
Yeah, it's just like the pressure
Okay.
that's on each side of it. And since we have this thing open to the atmosphere on each side, you've just got atmospheric pressure
Okay.
on both sides. So you can just forget about those two unless you have a pressure differential. Like if I said that one end of this was under pressure and the other end wasn't,
Okay.
then you would need those there. But right now you don't even need those there.
Okay.
All right. So and another way to look at this is, how we're using this as conservation of energy, right? So what happens? So did we retain the same units is kind of like an important question here, because if we're using conservation of energy, but we don't have joules that we're working with, then it's not even energy, right? So it's kind of an important checkpoint to make sure you did something that's okay. But since we divided both sides by volume, we were already in joules, and we divided both sides by volume. We can just
Yeah. It's
multiply both
still
sides
gonna.
by volume,
Yeah.
right, and get back to joules. Yeah.
Yeah. Okay.
Okay. Cool. So, all right. So, does this all sort of make sense? I know I'm just kind of like blowing through it really quickly,
No. No.
but
No. It does.
okay. All right. So then, what you're able to do is think of, okay. So now, how do you think about this? Like, how do you think about some of your variables? Because again, we're trying to solve for how fast the water's shooting out of the thing at the end.
So you're
Right.
solving for V2. So
Yeah.
you could algebraically solve for that,
Mm-hmm.
which would be the density GH1 plus 1/2 P, or density V1 2.
I wouldn't mess with that yet until you until you have eliminated some, because you can eliminate some of these things here before you
Oh, well,
start
the
solving
density
for it
is
algebraically.
going to be same. all of
Right.
everywhere.
Yeah. Exactly. So you can just kill the density in every single one of these, and also the density of water is just 1 gram per milliliter or 1 gram
Yeah,
per centimeter cubed. Yeah. So yeah, you knock out the density.
and then
All right.
now you can solve for V2.
Okay. Yeah. Do you have all the other variables?
You have your original height. Well, you can't say your original height because the water's flowing continuously, right?
You can, so now, but now that we have said, now that we're looking at the entire column of water, you can actually say the original height as long as you just take like the highest point.
So then
Right.
that would be 10 meters.
Right. Exactly. Yeah. So you could say height 1 is 10, right? H1,
Hmm.
let's say H1 equals 10 and H2 is 4, right?
Yeah.
But you can make that a little bit easier on yourself because this is all relative. And so you can assign what 0 is.
Yeah.
0, like 0 doesn't have to exist right here. 0 can exist right here. So you could just say
That
that,
H2 is at 0.
right. Yeah, exactly. Height. So then height 1 would just be 6 and height 2 is 0,
Okay.
right? And so once you've made height 2 0, then you get rid of that whole expression right there.
Okay.
Right. Okay. So then, yeah, so then you've got 6 for the height 1. All right. What about velocity initial? Because that's pretty much like the last thing that you don't know at this point, right?
Yeah.
Okay. So what could you say about the initial velocity here?
Um well, um there is initial velocity, right?
Where is it?
It's at it's at the start of the pipe.
Right. And it'd be, like in this direction, obviously,
Yeah.
right? Because it's the
Downwards.
only way. Yeah. But what can you know about that velocity versus this velocity of the fluid exiting? Which one's bigger?
The first velocity, wouldn't it be?
Well,
Mm,
so if you look at this is called the continuity equation here.
mm,
And so anytime you've got fluid flowing through a pipe, the fluid, you're going to have the same volume flow rate at each point along the pipe as long as it's continuous, right?
mm.
Otherwise, you would get like either a pressure increase or pressure decrease somewhere in the middle of the pipe, and it would either, the pipe would either explode right here or it would implode. The walls would
Yeah.
collapse in if the pressure decreased, right? So that you have the same like liters per hour or whatever flow rate at the beginning and at the end. However, at the beginning, your area is much greater, right?
Yeah.
Because if you're gonna have if flow rate, if like liters per hour, you could say like volume, we could say like volume per time, volume 1 per time, or well, volume per time, yeah, volume 1 per time divided by is equal to volume 2 per time, right?
Right. Yeah.
Yeah. And so another way of thinking about that, well, rather than volume per time, we could also think about it as area, right? Area times velocity. Because
Okay.
if you take area times velocity at any given point, then like cross-sectional area times
Yeah.
velocity at any given point, that's the same as volume flow rate
Okay.
at any
Yeah.
point.
Okay.
So
That makes sense.
yeah. So you've got like A1 times V1 is equal to A2 times V2. And this is called the continuity equation. Okay.
Mm,
And all right, so then what's your A1? Well, this is 5 meters across up at the top here.
mm.
So your radius, so what's your area up there if it's 5 meters?
Um. And it's cylindrical, right? We're calling it cylindrical.
Yeah. So it's just like the area of that circle or of that cylinder.
Um, s- uh, the pi r squared is for a circle.
which is perfect, right? Because
Okay,
it's
yeah.
if it's cylindrical, then the cross
Yeah.
sectional area is a circle.
Is this,
Yeah, yeah. So you've just got pi times 2.5 squared, right?
Yeah.
Because the diameter is 5.
Okay.
Yeah, and I wrote that about as messily as I could. This thing seems like it's writing extra messy today, but whatever. Yeah, so pi times 2.5 squared, right? Times whatever v1 is, right?
Mm.
And then on this other side, you've got your diameter is 0.01 meters.
Mm.
So you've just got pi times, I guess your radius is 0.005
Yeah.
squared, right?
Mm.
Times v2. Okay, and so something you can look at here, well, first of all, you can cancel out the two pi's. They cancel each other. And then you can see that if you can divide one side by the other, and it really doesn't matter which way you do this, but you can pretty quickly see, well, first of all, this is going to be 2.5 squared is like 6.25 times v1, and then 0.05 squared is something really small, right? It's like, I don't know, so that would be 5 times 10 to the negative 3, so it'd be like 2.5 times 10 to the negative 6 or something like that. Point is, it's really small. So if we divide 6 by 2.5 times 10 to the negative 6, we end up with it's several million times greater, right?
Yeah.
So what this is ultimately telling you is that v2 is, I guess I'll go ahead and say, I'll just say 0.05 squared. So what this is just telling you is that the velocity 2 is much greater than velocity 1, right?
Yeah.
So much greater, in fact, that we could just say velocity 1 is 0.
Okay.
Yeah, so that's my point here. And so this is something that is hugely important to be able to recognize, and I can't give you like a hard and fast rule on specifically like how to recognize it, but it's something that I'll emphasize when it comes up, and you'll see it as it comes up in practice questions and stuff over the course of time, so that when you get to the MCAT, you'll be able to pretty predictably be able to pick out situations where you can just make a variable 0 because it's close enough to 0, right? And where you can't do that is like if you're dividing that variable by another variable, or or if you're using that variable and dividing another variable by it, then obviously making it 0 is a problem. But well, but you seem to be really good at math, and so I don't think you'll have any issue determining those situations. Some people get pissed whenever I tell them that I can't give them like a hard and fast rule on when they can do this, but it's super helpful when you can, because it makes really complex equations super duper simple.
Yeah.
So, okay. So then at that point, once you've done that, you eliminate this initial velocity component, eliminate that 1/2. So now all you're left with is G times H1 is equal to
1/2 V2 squared.
1/2 V2 squared, which is super simple. All right.
Okay, so then that would be 20 times 10.
20 times 10.
Square root of 20 times 10.
Square root of 20 times. I don't know where you're getting that. Sorry.
Because I just solved for
you
V.
skipped through it. You skipped a bunch of steps, I'm guessing. To do that. Yeah. Okay. Gotcha.
I solved for V, and then you would get the square root of 200. Or
is it 200?
Because you said the height's 10.
Well, the height was, remember we made.
Oh, we set 0 down, so that's 6. Okay, there we go.
Yeah.
I had moved my 0 back down. But then that changes a whole bunch. That changes us eliminating stuff. So then that's 120. The square root of 120. Yeah. Okay.
Right. Yeah. So radical 120, which what is radical 120? Off the top of your head, as quickly as you can.
It's not coming. Not today.
Okay. What's the square root? Or what's 10 squared? 100, right?
Yeah.
11 squared.
121.
Yeah, which is really, really close, right? So we could just say 11.
Okay.
Yeah, I was just, just kind of emphasizing like ways to do math really, really quickly.
Okay, cool. I'm sorry.
Oh no, you're
really
good. I know
slow
you've
right
been up for
now.
30 hours. Yeah, I know. Yeah, so I'm just trying to emphasize, like, the MCAT is really, really, really likes to reward you for being able to approximate appropriately. You know,
Okay.
knowing when to round off versus when to get a precise answer is important. And this is a good example of an instance where it's beneficial to be able to round it off. So there you go. Yeah, so it's coming out at 11 meters per second squared. Or I mean 11 meters per second.
Cool.
All right, cool. So that was what I wanted to emphasize there, just like different ways of thinking about the conservation of energy, and specifically, it's really helpful in fluid dynamics to understand Bernoulli's law. That's what this is.
Okay. Cool. Thank
Yeah,
you.
so we can say, oh yeah, no worries, no problem. Bernoulli's. This is one of the I stole this, borrowed, whatever. This from Kaplan, because this is one of their things that they walk people through during this component of physics. Bernoulli's law is just conservation of energy or fluids specifically, and that's probably the way that you're most likely to see conservation of energy explicitly tested on the MCAT, just because it's too easy for them to ask you a question about a ball rolling down a hill. They're probably not
Okay.
going to do. Yeah, they're going to do it like this because it just makes it more complicated and they want to make it hard. Okay. Another idea in fluid dynamics is really difficult for people. I'm going to try to do this qualitatively rather than giving you numbers to solve and stuff, just because it would take too long for me to make up a problem that works out well. But imagine you've got like a fluid flowing through this pipe that looks kind of like this. Okay, and so it's the thing is completely full, but it has these little columns off of it along the way at various different points. I wish this eraser worked. This is ridiculous. Okay, there we go. All right, so it's got these columns at various different points, and in each of these columns, there's going to be room for the fluid to go up into the column. And obviously, if the pipe's full and this thing's under pressure, let's just say that the fluid's flowing this direction through the pipe. Where is the fluid going to be flowing through the pipe the fastest? Where will velocity be the greatest along this pipe? Just like left to right velocity.
It would be the left.
Which spot?
So, sorry.
Usually we got like sites 1, 2,
Okay.
3.
Velocity would be greatest at I'm just gonna say 2.
Yeah, exactly. Because remember that continuity equation.
Because the area is smaller there.
Yeah, exactly. Perfect. I drew this equation wrong, but yeah. Yeah, because of that equation, again, the velocity is going to be greatest where the pipe is the narrowest, right?
Yeah.
Okay. So then imagine in each of these, so because this is under pressure, there's going to be fluid going up into each of these columns. Let's say that one is up to that height, right? So fluid is going to fill these columns up to some degree.
Yeah.
All right. So then the next question would be, which of these columns, 1, 2, 3, 4, 5, is going to have the highest fluid level versus the lowest?
2 would have the highest.
2 would have the highest? Why is that?
Just because I'm thinking since velocity is greater here, that this would fill up quicker.
Okay, I see what you're saying, and that's everybody's intuition. Everybody thinks that here, but it's the exact opposite.
Oh.
Okay. Yeah. No, I know it's really weird. This every time I teach this, I'm like, are you really serious? You know, like it just seems super counterintuitive, and it's super counterintuitive. And so the way to think about this, the way this actually works, is that when fluid's flowing, when anytime you have a fluid flowing, when I say fluid, keep in mind that doesn't just mean liquids. Gases are fluids also. Okay. So anytime you've got fluid flow, then there's going to be a total pressure. And that total pressure is going to be comprised of both static pressure and dynamic pressure.
Mhm.
Static pressure is just the pressure that, like if the fluid's standing still, that it exerts on the walls of its container. Okay. Whereas dynamic pressure is the pressure propelling it to flow from one place to another place. It's very, very analogous to potential energy and kinetic energy, with potential energy being kind of like static pressure and kinetic energy being like dynamic pressure. So in the spots where the fluid is flowing with greater velocity, then you're going to have more dynamic pressure and less static pressure.
Okay.
So here, dynamic pressure is bigger. In
It's
this
higher.
is higher, right? Yeah. So here you've got like dynamic pressure is increased, so static pressure decreases, right?
Okay.
And so I just realized that I drew it the way that you told it to me, not the way that that it actually is. So
So
yeah,
then
so
that means that's gonna fill up the least because the dynamic pressure is higher.
at the other points, right?
Yeah.
Yeah. So oh, I'm sorry, dynamic pressure is higher here, right? Yeah. Sorry, I can't hear. So yeah, dynamic pressure is higher here, meaning that all of the pressure is pushing the fluid left to right rather than up.
Okay.
But because velocity is slower over here at 0.1, then dynamic pressure is greater. Or I'm sorry, dynamic pressure is lower and static pressure is higher.
So
So
what?
the fluid level goes up higher. So at points like 1 and 5, the fluid level will be high, and at 0.4, it's going to be a little lower, right? And at
Yeah.
points 2 and 3, it's going to be the lowest, because these are the points where dynamic pressure is the greatest and therefore static pressure is the least. So
Okay. So, quick question.
yeah, go ahead.
So, in this setup we've drawn here, are 1 and 5 gonna be equal static pressures?
Mm-hmm. Yeah,
Okay.
yeah. Assuming that they're the same, that their diameter is the same,
Okay.
right? Yeah. So if we say that this is like, I don't know, 5 meters and this is 5 meters, then 1 and 5 are the same.
Okay.
Obviously, if one of them's 6, like now this is 6 meters, well, then one is going to have less dynamic pressure, therefore more static pressure, and so it would be higher than 5,
And then,
or vice versa.
if these, columns, these extra tubes shooting out of the system, if they were different, areas, how does that
Oh, good question. I have to think about that for a second. Uh, that's a really good question. I I
might
want to say it doesn't matter, but that doesn't seem right to me. So,
because I'm just trying to think, because like, if one's a smaller area, so it has a smaller diameter entrance, then it
mhm.
has more dynamic pressure in that one little section, which means less static pressure, right?
Yeah, that's a really good question. I need to look that up. I think
Okay, because
my
it just seems like reverse there.
yeah. My intuition is that the height that the vertical columns. Hmm. I'm gonna say that if the vertical column is wider, I want to say that if the vertical column is wider, that it goes up higher than if it's not as wide, because if the vertical column has less area, right? If it's a narrower
Yeah,
vertical column, then that column is going to naturally have greater pressure inside of it, right?
yeah,
Because that's just how, that's your other equation, your Poiseuille's law, or however the hell you say that.
yeah.
How, like, yeah. Okay. But that's a really good question. I haven't had anybody ask that before. Perfect. That's, yeah, great question. Sorry, I can't give you a
No,
confident
it's
answer right now.
okay.
I'll think about it. Here, I'm gonna scroll and write this down. Things I need to look up. Oh wait, that's a different page. Awesome. Okay. Um, find how the vertical column. What would I say? Vertical column diameter x column fluid level height. Okay. Yeah. Yeah, because I can't be sure. I'm never gonna BS you if I'm if I'm
Okay,
not
no.
sure, because that just leads to more confusion. So apologies there. But yeah, great question. Um this applies also really importantly to to airplane flight, which you may have read about. I don't know how recently you read that chapter, but it talks about like how airplanes stay up in the air at some point. Do you remember mentioning that?
Very briefly.
Okay. Yeah, because it talks about how airplanes stay up in the air, and it's really important. And this is like absolutely essential for like airplanes staying in flight because you've got like airplane wings, right? So here's your airplane. Here, there we go. Okay, airplane.
It has to do with something with Bernoulli's equation, right?
You can think about it from the perspective of Bernoulli's equation. You can also think about, I mean, Bernoulli's equation is the best way to think about it. Bernoulli's equation is just probably the most important fluids equation, period, just because it's conservation of energy, and conservation of energy is the most important thing, period. So, yeah. But anytime you've got an airplane wing, you have this weird situation where the front of the airplane wings are like kind of wedge shaped. And this is like if you're looking at the wing from like this angle. See what I'm saying?
Yeah.
But, so if you're looking at it from like the side, then this is the front here, and this is the back over here. So whenever the airplane's flying through the air, obviously the airplane's moving this direction. And so air is moving the opposite direction against it. And so air's coming this way against the airplane wing, right? So the air that goes over the wing is going to travel a very different pathway than the air that goes under the wing. So the air that goes over the wing has to travel that distance, whereas the air that goes under the wing travels this distance. They have to make that trip in the same amount of time. Therefore, the velocity of the air that's going over the wing is greater than the velocity of the air that's going under the wing. So therefore, dynamic pressure is greater on top of the wing than
static pressure on the bottom.
So static pressure is greater on the bottom of the wing, and so that's what generates the lift that keeps airplanes up in the air.
Okay.
And so this is called the Venturi effect. This, as well as the fluid level thing up here, this is called the Venturi effect. When greater flow rate leads to lower static pressure.
Okay.
It was really counterintuitive, but for that reason, likely to be tested. Okay. So do you have any equations? I was reading the word equation in the book over here. So do you have any questions on that stuff?
No, I think I get this after
Okay, cool.
the whole problems we've done.
Okay, cool. All right. So if it's okay with you, unless you have other questions or anything, then definitely let me know if you do. I want to jump over to talk about some of the equilibrium versus kinetics stuff.
Okay.
Okay, cool. So let's imagine for a second we've got some chemical equation. What is this? Okay, some chemical equation that is, let's just say we've got like A plus B. Yeah, let's just go A plus B yields, or is that equilibrium with C plus D? All right, so how would you write out the equilibrium constant for this reaction?
It's products over reactants.
Right, okay, yeah, so KEQ, equilibrium constant, is equal to products divided by reactants, for sure. And I'll just write concentration products divided by concentration of reactants. Okay, and so how can you tell just by looking at the value for KEQ which one's favored, products or reactants?
If higher KEQ favors products.
Okay. Yeah, so higher KEQ favors products, right? So if KEQ is greater than 1, then your products are more thermodynamically favorable than reactants are, right? And vice versa. Okay, cool. So that's KEQ. So then what about Q? Do you remember what Q stands for here in this context? The reaction quotient?
That's the I know I don't know how to put it in words.
Okay. Yeah, so what we were actually just talking about with KEQ is really actually Q. So Q stands for, again, Q equals reaction quotient. Quotient just meaning, when you divide something, right? And so for every single reaction, whether you're at equilibrium or not, there's going to be some Q, right? Some Q value. And it's just the concentration of your products divided by the concentration of your reactants. That's all Q is. Okay. And so KEQ is really just a specific instance of Q. So if Q is equal to KEQ, then you're at equilibrium. Does that make sense?
Yes, it does.
Okay, so if Q is equal to KEQ, that tells you you're at equilibrium. What if Q is not equal to KEQ? What does that tell you about the system if Q is not equal to KEQ?
If Q is greater than KEQ, then it favors the reactants, and if Q is less than K, it favors the products.
Okay, great. Yeah. So if Q is greater than KEQ, then your system is going to move toward reactants, right? Naturally,
Yeah.
unless you're messing with it in some way. Okay, and so what this does is it allows you to predict what's going to happen anytime you mess with any system, right? So if we say that our equilibrium constant is 10, but we've got a Q of 1, then we know that we're going to move toward products, right? Okay, and so because something that the MCAT loves to test is Le Chatelier's principle. Do you know what Le Chatelier's principle is?
Yeah.
What is it?
So slow today.
Oh, you're good. Don't worry about it. And the reason I ask you these questions all the time is twofold: to both assess where you are, that way I can know what to talk about, because if you know something perfectly, then there's no point talking about it. And also just to challenge you to generate it, because if you can generate something, like if you can explain something, then you really know the shit out of it. But
Yeah.
because you allow yourself more leeway in your head than you actually have, then it's actually available to you. So saying something out loud is like the best way to learn it, in my opinion.
Yeah. No, I I know the factors of it are like concentration, pressure, temperature, and then inert gases. I know those are the factors. And it's like I remember like if you have a chemical equation and then it's like if you do this to this side, which ways it's gonna go.
Okay, yeah, that's a good way to think about it. Yeah, that works. Okay, yeah, so I would say Le Chatelier's principle is just like the chemical equation is always going to move toward equilibrium, and so if you mess with it and pull it out of equilibrium, it's going to respond so that it reachieves equilibrium. Yeah. So that's really, I'm not going to type all that. But Le Chatelier's principle, like I said, is just the system trying to achieve equilibrium, and so it's really easy for people to kind of get caught up in this idea of, okay, so we removed reactants, so that means we're going to make more reactants, which is true. Or we made more products, so that means our system's going to move back toward reactants, right? Okay, sure, true. But I think it's just a lot simpler just to think system will always move toward equilibrium. And so if you screw with the system when it's at equilibrium, it's going to respond in the opposite way that you messed with it. Right? And so the real benefit of thinking about that more abstract definition, well, one, it's just less stuff to memorize, because then you could just know, like, to predict that the system is always going to move toward equilibrium. But two, it protects you from the situation where they give you a system that's not at equilibrium. And then, so let's say, here, let me think of an example. Okay, let's say that your KEQ is 10. All right, so KEQ, again, we'll say is 10, but here your Q is let's say 10 to the negative 5. Okay. So you know these two things about the system. And then you come in and let's say that we remove, let's say we remove 1 mole of A. So we remove 1 mole of reactant A. So which direction is this thing going to go?
Doesn't that depend on the coefficients of your reactants and products?
That's fair. Okay, so well the thing does depend on the coefficients, right? So if you let's just say that they're all 1 for right now.
Okay.
But it doesn't actually matter here because the system is always going to move toward equilibrium, right?
Yeah.
Okay. So so you can always know that Q aspires to become KEQ. KEQ is like Q's hero. And so the system's always going to behave so that Q can become more like KEQ. Okay, so if you got this really small Q and really big KEQ, you come in and you remove 1 mole of A. So what's Q? Is Q going to get bigger or smaller when you remove 1 mole of reactants?
It's Q. It's gonna get bigger.
Oh, I just realized that I screwed that up. That's fun. Okay. Damn it. Hang on one second. I'm lost. Trying to do this in my head. Okay. Yeah, that's fair. Yeah. So yeah, Q is gonna get bigger. Now I see why you said you need to know your your coefficients. I got you. Okay. I meant to put this the other way around. So my point being though, that if you like, okay, so because most of the time people would think, oh, well, I've removed reactants, therefore the system's going to shift back toward the reactants, right? But that's only true if the system's at equilibrium. Yeah. So here, what I meant to do is just give you a KEQ and a Q that were really far apart and then mess with the system negligibly. And the result is that we're still going to move toward equilibrium, even though you would predict that we would move in the opposite direction because we removed reactant. Right?
Okay.
But, yeah. That was kind of like the the gist of the example that I was giving. I tried not to make up examples on the spot like I just did for that exact reason. It's just kind of hard to reason through every nuance of it on the spot. But so apologies for that. But point being that it's a lot better to think about Le Chatelier's principle in the abstract, meaning that Q will always try to become KEQ rather than thinking about specific instances of the thing. Okay. So
in this case, Q is going to get bigger to try to become KEQ.
Yeah, exactly. Q will always move toward KEQ.
Okay.
That is something that is always true. It's Q will always, unless you're messing with the system, right? You know, like unless you're actively pulling it away, Q will try to move toward KEQ.
Okay, so then in this example, wouldn't it favor the reactants then to try, because Q is going to get bigger to try to meet equilibrium? So it's good this situation, it would try to produce more reactants. That way it could balance out to KEQ. Because the more reactants you have, the smaller your Q and KEQ are.
So in this situation, we're gonna produce more products so that Q can get to KEQ. Right? Because this is 10 to the negative 5.
Oh, okay.
See what I'm saying?
Yeah.
Yeah, that's a bad. It's not that part of it's not necessarily bad, but my example I should have come up with this earlier, but I hadn't used that specific example before just because I'm coming up with you seem really on top of this stuff, so I'm coming up with harder instances, and so that's why I didn't have that example pre-made. But yeah, so you see what I'm saying though? Your system's going to move toward the right, toward the products because your Q is much smaller than your KEQ here. So we need to make it bigger. It needs to get bigger. So we need to make more products.
Okay, yeah, that makes sense because more products and you divide it by the reactants. So if you have more products, it's a bigger, okay.
Yeah. So we need to turn reactants into products. So we'd be removing reactants and making them products.
Okay, that makes sense.
Yeah. Okay, cool. So, all right. So then if you think about that graph that we were looking at a second ago over here, this thing right here, where does your equilibrium sit on this graph of this specific problem, or like of this specific thing? Because like we're looking at if we're saying again, this is A plus B at equilibrium with C plus D, then obviously like A and B are over here, right?
Mm.
And C and D are over here. So where's your equilibrium going to sit?
It's gonna be at the middle of the slope of the line that's going down.
So like we'll just say that we're looking at the blue one here because
Yeah.
this I made this for like an enzyme thing.
Okay.
Yeah, so this is not. It's a lot of this is like we're not talking about activation energy just yet, but so you're saying it's gonna sit like right here in the middle?
Yeah.
Why? Specifically?
Because I remember doing acid-base chemistry and titrations, and
Okay, so this is very different than this is kind of related. This is peripherally related to that. I don't want to say it's not related, but these two graphs are generated very differently. And so what turns out is that in this specific example, the equilibrium is going to sit right here.
oh, because it's greater. Okay. Okay.
Your equilibrium exists at the lowest point on the energy graph always.
Okay.
Because that's like the definition of equilibrium.
Okay.
So, yeah, I'm writing equilibrium exists at lowest total energy, we could say. Because that is what an equilibrium is. It's like the energy minimum of the system.
Because the system will always strive to go towards lower energy rather than higher energy.
Perfect. Exactly. Thank you. I I love that. When I like it whenever people get stuff really quickly. So
Okay.
yeah, awesome. Yeah, absolutely. So what that tells you is that this graph is bullshit for the most part. Like people, and it really is. It's not really bullshit. It's just like an oversimplification. What the graph really should look like for most chemical reactions, because most chemical reactions don't go 100% to completion unless you drive them that way by removing products, right? But what most chemical reactions would probably look like is something like this, so that your equilibrium is not all the way toward products.
Yeah. Okay.
Yeah, so that's how most reactions would in reality look. I just didn't want to complicate my enzyme discussion by throwing that in there. So
Okay.
yeah. I'm making this for like because I'm trying to create like an online portal with a total curriculum full of videos, the instructional videos that people can buy rather than purchasing tutoring hours if they don't want tutoring hours. So
Okay.
that's what I'm making this for. But anyway, I just wanted to use the graph because it was pretty and it also does. I think that noting this is really helpful.
Okay.
Just know that the equilibrium will always exist at the lowest point. So some systems might even look like, obviously you can have some reactions that are not spontaneous. So, it might look like that. But in reality, that graph is wrong, because what the thing would probably look like for a non-spontaneous reaction would be something like that, because you would have some low point that's not, that's not
All products.
That's not all products, right? Or not all reactants also. Yeah.
Just a quick question
Mm-hmm.
on the end, because I'm looking at this and I see enzymes.
Yeah.
Doesn't the body isn't the body like a driving force for the enzymes to go to produce products? So technically, it doesn't typically have 100% completion rate unless something's wrong.
I'm sorry. So you're saying the body is like a driving force for?
Yeah. Oh, wait.
Um.
Sorry. Thinking of something completely different. Ignore what I said.
Okay. Well, yeah. I
Describe it.
mean, it's not a bad question. It's a question that we can go way off into the weeds of enzyme kinetics and all that stuff on. Your body does a good job of. So if you do want reactions to go all the way to products, you can very easily do that. You just have to be removing product, right? Because if you remove product, then you shift Q back down below KEQ. And so you're going to make more product, remove product. Well, you make more product, because you're removing pressure from that side of the equation, as Le Chatelier's principle would predict. And so the body actually does a really good job of doing that in various different ways. For instance, you've got this equation going on constantly. Let me scroll down so I can have some room. Maybe I should go back over here to your thing on this. Let's just do it here. Okay. So you've got this equation going on constantly in the body to regulate your pH, your blood pH. Okay, because your cells are always producing a little bit of acid as a byproduct of metabolism. Okay. And so you can regulate blood pH by turning it into CO2 and breathing it off.
Yeah.
Okay. So the acid that is floating around in your blood is H2CO3, carbonic acid, and that's going to exist at some equilibrium with CO2 plus H2O. All right.
Yeah.
And so you're always going to be breathing off the CO2, right? Expire this. So you breathe this out into the atmosphere. And so that shifts it toward the products always. And you do that all over the place in the body so that you really are pulling things all the way to the products continuously. So that's a good
Okay.
question. Yeah. I don't know if that's what you meant to ask.
Yeah, no, it
but
is. So the graph
but that is.
technically isn't BS for the
No, it
enzyme
wasn't
question.
BS. It was a good
Okay.
question. Yeah, it was a good question.
Okay, sorry,
And
that was a side note.
yeah, no, you're good. And I'm happy to go down any side notes anytime because, well, I mean, that's gonna like define our discussions later in your process. Like the second half of your prep process is gonna be all running off down like tangents because everything's interrelated. Everything on this entire test, except some of the car stuff, is totally interrelated. And so so like later on we'll try to hit as much shit in each discussion as we possibly can, and we won't have like set like 4 or 6 or 8 chapters governing what we're trying to cover. We'll just like explore random shit all the time. But there's probably enough here in all in the stuff that we are covering just to stick with that. But like I said, I'm happy to discuss whatever you want whenever you want.
Okay, thank you.
And like if you have a test or something, like if you have a test in one of your classes and you're needing to study for that, then we can talk about all that stuff too in any of our meetings. Like I'm happy to go over whatever you want to go over. And so I've had people find that really helpful before, like in a week where they have an exam, they'll not want to meet, and I'll be like, well, this is MCAT relevant stuff. Let's just talk about that rather than what we were planning on doing. And it tends to work out pretty well. Okay, so
Oh,
go ahead.
real quick. I'm sorry. I just remembered a physics question I had.
Okay, cool.
So with like with Zeroth law, like A is equal to B, B is equal to C, and A is equal to C of like energy transfer.
No, I have no idea what you're talking about. Sorry. Let me
like let's say you have like a cup of coffee, right? And you have a spoon. And then like it's like thermal equilibrium. There we go.
Oh, zero with law. I was like,
yeah.
what are you talking?
I can never pronounce things when I read them.
Oh no, you're good. You're good.
Zeroth law. So how does like that apply to like this is just like a thing I was thinking about when I was reading. How does that apply to like electricity? Because is electricity count as like a point of contact, or is it transferred heat through the air that heats up the other side? Or
good question. Electricity has nothing to do with heat. That's a misconception for people a lot. Okay, but what does happen is that you have resistance to the flow of electrons, because electricity is just movement of electrons through from one side of a metal to another side. And so at temperatures above absolute zero, you have resistance to flow of electrons because the atoms in that metal are going to be moving a little bit. And so there's going to be some points where the electrons have a hard time jumping across because the atoms just vibrate apart and back together. At absolute zero, they stay still. And so electrons can just hop across with no resistance at all. And so there is no heat generated at absolute zero. And so the reason things heat up when you move electricity through them is because of that resistance to the flow of electrons.
Okay, that makes so much more sense now.
Oh yeah. Okay. This is gonna be really fun. As you start to learn all of this stuff, you're gonna see like, holy shit, everything is interrelated. Like it's all one thing. It's really super interesting, in my opinion. But then again, I'm the person that's teaching this for a living. So maybe I might find it more interesting than your average person.
No, that's super cool. Okay, thank you. Sorry, back to chemistry.
Oh yeah, no. Yeah, no problem. No, that's a really good question, and we'll cover a lot about electricity and how electricity works and all of that stuff, which I'm guessing you know some about right now, just because it seems like you like to do mess with stuff like that. But we'll cover that in detail for sure. It's later on in the physics section. So did that actually answer your question though?
Yeah, it did. It did.
Sure I did answer the thermal equilibrium thing.
Thank you so much.
And thermal equilibrium is really just like another, it's like another instance of entropy, because it's just like like if things are in contact, then that energy is going to spread itself out as evenly as possible.
Yeah.
Yeah. So, yeah.
Okay, thank you.
Yeah, no problem. And in reality, like all mass is actually energy as well. Are you aware of that idea?
Very briefly. I
Okay, yeah. We'll talk about it later in some of the physics as well. It comes up relativity and all of that stuff. But mass
Okay.
is actually just like a gigantic concentration of energy because of the Einstein equation, the E equals mc squared. So you, if you wanted to decompose your atoms that make up you, you would find out that your mass is actually just like massively concentrated energy, and the relationship between those two is the speed of light squared. So
Okay.
yeah, so like 1 kilogram of mass. So if you have like a 1 kilogram mass, you just multiply that times the speed of light, which is 3 × 10⁸, right? And that, and then you square it, and then you are that many joules. So, like 9 times 10⁻16 joules of energy is how many joules 1 kilogram of mass actually are.
Okay.
Yeah, which is a shitload of energy. Like 10⁻16 is a big number. So I just find that to be kind of neat. But
That is cool. Thank you for
yeah,
sharing
it's
that.
really cool. So, yeah. And so, like, as the universe expands, eventually everything will just dissolve outward because mass will just break apart into
Yeah.
energy. Yeah.
Okay, cool. My friend, my roommate, one that's over in that past that wall over yonder
Oh,
there,
yeah. Yeah.
was a quantum physics major.
That's really cool. He probably knows far more about this shit than I do.
I asked them to help me when I was in biology learning about plants and how they bounced photons around on
Hmm.
their leaves, and I didn't
Yeah.
understand it, and they explained it so well to me.
Oh, really? That's
Yeah.
pretty cool. I mean, quantum physics is where it's at. Like that is probably the closest that we can come to ground truth right now. I think that there's something closer than that probably that exists out there, but I don't know what it is. So yeah, it's pretty trippy stuff. I love talking about that stuff. We'll get into it later. I'm tempted to dive into some of it right now, but you haven't done the reading, and so it'd be very self gratuitous, and I don't want to do that.
Oh,
Like that'd be for my benefit more than yours, and that's a dick move. So, uh, okay.
okay, really quick,
Uh-huh.
I'm trying to, like, look at stuff that I've written down that I might have questions on when I was reading the
Yeah, for
chapters,
sure.
and I didn't quite understand what when the Kaplan textbook said, this was on the, uh, chemical kinetics chapter, chapter 5,
Okay.
and it said, altering the concentration of protons affects not only the ability of an enzyme to maintain its secondary, tertiary, or quaternary structures, but can also directly affect the collisions between reactants.
It
I've
it said
never,
altering what?
uh, uh, but can also directly affect the
Um,
collisions
uh,
between reactants.
so it said altering what does that?
The concentration of protons.
Oh, so it's saying like pH when it says concentration of protons, I'm assuming.
Okay.
That's what it's saying. That's a stupid way for them to write that, but yeah. That's what it's trying to say.
Okay.
So
Oh, that makes
that's a bad way for them to write that. That's on them, in my opinion.
okay. Never mind. Question answered.
Does that make sense? Though,
Yeah.
because proteins have optimal pHs, and so if you raise or lower the pH too much, you're gonna denature the protein, and then the enzyme won't really do anything.
Yeah, okay. Completely makes more sense. I prot okay. Yeah, okay,
Yeah,
makes sense
that's
now.
that. It's a dumb way to write it. It really is, right? Because you're thinking concentration of protons. Is that, are we doing nuclear chemistry? That's
Do you
should be
know that's
something
why
like,
I was reading that entire section
yeah,
and I was like, why are we talking of okay.
yeah.
Okay.
That's interesting that they would do it that way. That's weird. Um, Overall, how did you feel about the chemical kinetics chapter? Because that was my next thing to talk about here.
Um I do need to do more practice problems on it just as a refresher, but I do remember a lot of it from Gen Chem.
Okay, cool.
Um,
Yeah, let
like
me.
I need to redo. I need to make like I just need to do more practice problems with it because I didn't do all the practice problems in this section.
Okay.
But like I remember doing the rate law, like determining the rate law, zero order, first order, second order.
Okay. Okay. So you do remember that because I was about to give you some a couple questions on that.
Yeah, I mean we can probably go through it.
Okay. All right. I think this will be worth it. This is going to be, I think, more useful for you. I'm going to start doing this for you more where I come up with some actual like questions to do because it seems like you're doing a really good when you're doing the prep, you're doing a really good job like actually getting through this stuff and retaining some of it because most people will read this stuff for the first time through and not remember any of it.
Hmm.
And so it's like I just reteach it. But if you're coming more prepped, then I need to have questions like this. So here we go. I have questions now. All right. So yeah, what's okay? Let's look. I was gonna skip 17, but let's look at 7. Can you see these well enough to read them?
Yes, all of
I
the
can also
following
zoom in more.
may
There you
be
go.
true concerning catalyst and the reactions which they catalyze, except uh A is true.
Okay.
Um,
Correct.
I think let's see, A is true. So this is asking which one is false.
Right. Right. Yeah. You're gonna see these questions all the time on the MCAT. So like, be careful with the all of the following except. It's so annoying. But yeah.
D is false.
D is yeah. Right. So D is the right answer here then. Right.
Yeah, because they lower the activation energy,
Mm-hmm.
and then they're not used up because I remember my high school Gen Chem teacher
Yeah. Yeah.
ingra- ingraining this into our brains, so they're not used up. You know, that's how factories are able to produce things so quickly with
Right.
like
Yeah.
only buying. And then
Perfect.
if you lower
Yeah.
the activation energy, then the reverse reaction is also lowered for that. And then so D's the only one left.
Yeah.
And
Yeah.
yeah.
Absolutely. Yeah. So I was just gonna emphasize over here that like delta G, meaning like things related to KEQ, because delta G says everything about the thermodynamics of a reaction, and
Mhm.
that's what KEQ is a comment on. So everything that is before this peak on the reaction, everything over here in this world has to do with kinetics, how fast the reaction is going to occur. Because the speed of the reaction has everything to do with how easy it is to get to that energy of the transition state.
Yeah.
Whereas everything post this line, post that peak, has to do with the delta G of the reaction or the thermodynamics of the reaction. And so catalysts are not thermodynamic things. Catalysts are only related to the kinetics of the reaction, therefore only care about the distance between the reactants and the activation energy.
Yeah. Okay, cool.
Yeah, perfect. So actually, and so how do enzymes really quickly, how do enzymes go about doing that? How do enzymes lower activation energy? If you don't know this off the top of your head, don't feel bad because it wasn't in any of your reading. But
Uh, they um they there's like I think of it as like a lock and key in my head, and then
okay,
like an enzyme will go, and then I forget what it's called, and then another thingy will come along, and then it like sits just right on the thing, and they kind of interconnect, and they're shaped so that only certain things, that only that molecule will lower the activation energy
okay,
when
cool.
present.
Yeah, that's. It sounds like you're giving the right description to me. So let me just add to it. And if I say the same thing that you said, I apologize. This may happen some. But I just want to make sure that I can add something to it. So so what an enzyme does is it has a certain affinity for the substrate molecule.
Mm,
So like for A and B in our A plus B equals C plus or yield C plus D, right? It has a
mm,
certain affinity for A and a certain affinity for B. And so without the enzyme present, A and B reacting with one another, the speed at which A and B are going to react with one another is going to depend extremely heavily upon the probability of A and B running into each other, right? And so if you increase concentrations of those two, the reaction is going to obviously go faster because there's going to be a greater probability that they just happen to run into each other and exist in the same space at the same time. But if you put the enzyme there and the enzyme has an affinity for A and an affinity for B, then whenever A encounters the enzyme, it's going to stick to that enzyme. And so A and B don't necessarily have to occupy same space at same time, or they still do, but whenever A occupies a space, it's going to stick onto that enzyme, and then we're just going to wait for B to show up, and that's also going to stick. See what I'm saying? So the enzyme just increases the probability of those two existing in the same space at the same time necessary for the reaction. And it also will have an affinity for A and an affinity for B, but it has the greatest affinity for the conformations of A and B that are most conducive to the transition state. So most of the time an enzyme is going to bind a version of A that has some bond strain that facilitates that reaction happening, right? So it won't bind like the most energetically stable form of A, if that makes sense.
Yeah, it does.
Okay, cool. So what about this one?
Oh boy, my favorite.
This is the consummate rate question. So yeah, that's why I grabbed these questions actually.
Okay. So I've lost my tab. There we go. So you're gonna look at where, you're gonna look at where, like, you're gonna look at all the trials, right? And then for molarity A, I'm gonna look at points where the molarities are the same, and then look at molarity B, and then oh, what's the equation?
The rate law equation. I can just give it to you.
Yeah.
Yeah, so it's going to be rate is equal to some rate constant, K, times the concentrations of the reactant. So for this equation, it would be, well, what would it be for this equation? Forget the data for a second. Just think about this specific equation. Assume it's an elementary reaction. So you've got A, concentration of A, and concentration of B, both present. But then you also have to raise them to how many molecules there are present.
So then A is 2, and then this would be a third order reaction.
Yeah, if that's an elementary reaction. Okay.
Yeah.
What do I mean by element? What's an elementary reaction?
Can you define that for me?
Yeah. An elementary reaction. This is nobody knows what this is. An elementary reaction is a reaction that, as written, like the equation as written, is what's actually happening on the molecular level. Another way of saying it is that an elementary reaction is just a single step reaction.
Okay.
So like SN2 reactions are elementary reactions. SN1 reactions are not. They're multi-step reactions.
Okay.
So if I were to give you the chemical equation for an SN2 reaction, the rate law would directly reflect that chemical equation. Same exponents and everything. If I give you the chemical equation for an SN1 reaction, that's a multi-step non-elementary reaction, the rate law for that will not reflect the reaction equation that I give you.
Okay.
All right. And so yeah, that's go ahead. What were you gonna say?
Just to further push out that, I've missed like one class of organic chemistry, but I'm trying to relate it to it. So we're converting like I'm forgetting my functional groups. Hold on. I don't have my sharing thing shown up. I'm gonna use the whiteboard. That will help a lot.
Okay, yeah, go for it. I can stop presenting too if you need me to.
I don't have my, you know how I was sharing my screen last time? I don't have that set up right now.
Oh, you don't have that? Okay, gotcha.
No, because my tablet died at school today, so I was like joining and it's plugged in right now.
Right.
Okay, cool. Can you see? Okay, so it's like you have, like this, right? And you're reacting this with Cr2 so O something, or like one of these like oxidation thingies, and then this is
Hmm.
becoming. Obviously, you have like a functional group here, right? Or like the rest of the molecule, and you're converting this
Yeah,
to a carboxylic acid. Is
yeah.
this what is the like rate? Do you know the rate law for this? Like if it's an element, if it's multi-step? I missed the day where he went over the mechanism.
That's a good question. I'm not sure. I need to
Okay.
look it up. Yeah, I don't remember that. Those oxidizing agents are kind of weird. You know, anything with a metal in it, anything with a transition metal in the reaction is weird, and a lot of them, the mechanisms aren't actually known, and I'm not sure if this is one where the mechanism is known or not. I know you don't need to know it for the MCAT,
Awesome.
which
Great.
is
That's
well,
all I
yeah,
needed to hear.
yeah,
All I
yeah.
needed to hear.
You do need to know what the products are, but you don't, like you do need to know this reaction as you drew it, but you
Yeah.
don't really need to know how it happened. And
Okay.
I don't remember ever learning that either. So
Okay.
so it might be a thing that people just don't know. Yeah, or
Okay.
that you're not expected to know.
Okay. I just wanted to ask, trying to help set things in by relating it to things I'm currently also
Oh
learning
yeah.
about.
Yeah, no, you're good. But yeah, that is the correct answer of what comes out of that reaction. Yeah, it oxidizes it to carboxylic acid.
Okay.
Um
Anyway, back
I
to this.
Yeah, and I can give you examples of this, but most of the time whenever you see data like this, what you
Mhm.
can assume is that they're probably giving you a multi-step reaction, because if you have an elementary reaction, you don't need data to determine the rate law. You can just look at the equation and know the rate law, right? Like
Mhm.
for instance, if I give you like A plus B yields C, and I tell you that's an elementary reaction, what's the rate law of that?
K A to the first power, you know, B to
Mhm.
the first power.
Right, yeah, exactly. Okay. But if I were to tell you that that's not an elementary reaction, then you have no way of knowing what the rate law is. And so then you need data to determine it.
Mhm.
Okay, just wanted to emphasize that one more time. So like if you see elementary reaction, ignore all the data, just like look at the equation, write it down. um,
Okay.
but here that's not the case. So here you actually have to use the data. So go back to where you were. I'm sorry for going off on that tangent, but because you were thinking through it the right way, right? I think you
Yeah.
said that looking at A molarity of A is the same in both trial 1 and trial 2, right?
Yeah. This
Okay.
always confused me up. I would always flip things around when I would do
Okay.
this in Gen Chem. But and then you would divide, um you would set the like you would have, since the two initial rates are the same on the side, so that's just 1 for the rate is equal to zero point 0.1 divided by 0.05. And
You
then
can make it.
the multiplier there, that's actually 2. The multiplier is 2, right? Yeah, 2. So then the
O for A.
yeah, and then it's 2 for A. Oh,
You don't have to do any calculations here. Just FYI. Right?
oh,
Because if
it's D, isn't it?
no, it's not D.
Oh, okay.
It's D if this were an elementary reaction, but it's not. Right?
Okay.
So if you look at trial 1 and trial 2, where A stays the same. Okay.
Yeah.
So if concentrations of A are staying the same between trial 1 and trial 2, then that tells you that any difference, we haven't looked at the rates yet, but any difference in the rate of this reaction from trial 1 to trial 2 is going to be purely a result of changing the concentration of B, right?
Yeah.
Okay. But we see that the rates are the same between trial 1 and trial 2.
So B has
So
no effect on the.
so that exactly. Yeah, that
So
means
then
that
it's just
B does not matter, which means that
then
C is wrong and D is wrong.
yeah.
Okay, so then if you look at A, then you can look at A and see, okay, well, we change A, we hold B constant, and even if we don't hold B constant, it doesn't matter, right? Because we know that B doesn't affect it. So we can
Yeah.
just look at 1 and 2, or we can look at 1 and 3. So from 1 to 3, we see that concentration of A is doubled, right?
Yeah.
How's the rate change?
Uh it's um increased from 1 to 3. Am I looking at that right?
Yeah, from 1 to 3. Yeah, the rate when the concentration is doubled, the rate
increases.
doubles, right?
Yeah.
Does it double? Yeah, it doubles. I had to think about that for a second. Yes, it doubles. Okay. Yeah, so it doubles there, right? So what does that tell you?
That changing the concentration of A has an effect on the rate of the reaction.
Right, and it tells you that A and rate are in a 1-to-1 relationship, which doesn't really
Because they're
matter to
both
you right
2.
now because
Yeah.
because neither is squared. You know, like if the exponents, the only reason that would matter is if one of these were squared, but neither of them is. So what I was just doing is kind of pointless, right? But I just wanted to emphasize it, just in case you had one where that was the case,
Okay, cool.
right?
So then B is the correct answer.
So if B is the
Where's
correct
the
answer, then your rate and molarity of A are the exact same number.
Okay. So then what is the point? Where's why does
The 0.1 is this.
yeah is the K is the rate constant? But how from the data where is that determined?
Well, look at how, so molarity of A, right? Molarity of A, 0.1. Initial rate, 1 times 10 to the negative 2, or you could say 0.01, right?
Mhm.
And so if you take the concentration of A and multiply it times 0.1, you get this.
Take the oh.
You see what I'm saying? And you could look at trial 1 also and say
You could also
0.05.
just since I know B doesn't have an effect on this,
Right.
it's just you could just solve for K because you have your rate and you have your concentration of A. Okay. It's okay.
Yeah, that's kind of a weird one. I hadn't seen one like that before this, and that's why I saved this question because I hadn't seen one like that. But like might as well factor in all the things that you could possibly be killed on. So and that's one of them for sure. I had to stare at that question for longer than I'd like to admit before I figured it out. I was like, what is this? And I realized, oh yeah, rate constant.
Okay,
Does that make
cool.
sense though?
Yeah, it does. It does.
Okay. All right, cool. All right. Oh, this is a good one, I think. Yeah.
X is the rate via a two-step mechanism as shown. X is the rate of step 1 and Y is the rate of step 2. If step 1 is much slower than step 2, then the rate of the overall reaction can be represented by so X is the rate of step 1 and then step 1 is slower. It's just X. It's A.
Nice. Perfect. Cool. Yeah, and so this is like the next component of the discussion on like multi-step reactions. So for an elementary reaction, like I said, the chemical equation just gives you the rate law. For a multi-step reaction, the rate you can still get the rate law from a chemical equation if you know what the rate limiting step is.
Yeah.
Because the rate law for a multi-step reaction will always be identical to the rate law for the rate limiting step of that reaction.
Okay, cool. Yeah, that's what I was thinking, is because like the reaction can't go faster than its slowest step.
Right. Yeah, exactly. So like if we wanted to write out the rate law for this reaction, you could say that the rate law is, well, this thing that we have written, which actually is, yeah, you could say that, well, if you were to assume that it was a single step reaction, you would say rate is equal to K times concentration of NO2 squared times concentration of F2 to the power 1, right? But that's not it's not an elementary reaction, so we can't do that. But we can say that the rate law of this thing is rate times, so you can look at slow step, right, which is step 1 here. So what would be this rate law?
NO2 bracket times F2.
Right. And so it's close, but we don't square the NO2.
Yeah.
Right. So that's why.
Will they ever not tell me which is the slow step and I'll have to figure out the slow step and then answer this question?
Yes, there. I can give you an example. Okay, here's an example. This reaction, actually, I can't. I don't want. I don't actually. I don't want to screw up this up by trying to make like
Okay.
an example. But here. So what I was gonna do is write out an SN1 reaction, right? So if I just write out some SN1 reaction, I don't have to tell you what the slow step is, but I can make you give me the rate law for it because the MCAT will expect you to know which step of the SN1 reaction is the rate limiting step.
Okay.
Right. So
Yeah.
like you could have, I guess an SN1 reaction could be like here. So you've got CH3 3CBr. So this is tert-butyl bromide plus, and I'm just gonna say like plus some nucleophile. All right.
Mm.
Negatively charged nucleophile. Yields, then you'd have your obviously your tert-butyl group stays there. You've got the C, and now you've got it bound to this nucleophile
Nucleophile.
plus your Br is left, right? So there's that equation, and I could tell you the MCAT would expect you to be able to tell me what the rate law is of this equation or of this reaction, even though this is a multi-step reaction, because you know what an SN or I don't know whether you know it off the top of your head right now, but whenever you take the MCAT, you'll know everything about an SN1 reaction.
Yeah.
And
The
so
rate determining step would be the nucleophile attacking the Br, wouldn't it? Or like the bond, and then like Br is the leaving group. And isn't the leaving group kind of fast? Hold on. Sorry.
oh, you're good.
Okay, there we go. I had a cough. I'm sorry.
Oh no, you're totally fine. Don't worry about it. Yeah, so it's actually the first thing that happens in this reaction in an SN1 reaction is that your leaving group actually takes off.
Oh, your leaving group takes off. I'm thinking of SN2.
Yeah. So your leaving group takes off, and so you're left with now you've got this C. I'll just write this.
And then it has a positive charge on the C, and then the nucleophile and the positive charge attract each other, and then it slams together. So your rate determining step is the leaving group leaving.
Yes. Yeah. The formation of the carbocation.
Yeah. Okay. Cool.
Is rate determining step. And so what would be the rate law of that formation of carbocation step?
Rate is equal to K bracket your tet butyl group, tet or whatever molecule name.
Yeah. Gotcha. Tert-butyl bromide. Yeah. And anything else?
No. I'm missing something though.
Nope,
No,
you're not.
that's it.
No.
Cool.
Yeah, you're good. Yeah. It's just a first order reaction, and you can know that because all that needs to you don't need the nucleophile to be there for that bromide to leave. Right? The nucleophile had nothing to do with that step, and so you know that it has to be a first order reaction because there's just one molecule falling apart.
Okay.
Yeah.
Okay. Cool.
Yeah. So that's how you can know that is a first order reaction, and so that's how you can know the rate law of a multi-step reaction without any data, just looking at the equation, because you know the reaction.
Okay, cool.
But if it's a reaction you don't necessarily like know the mechanism to, then you have to have data in order to determine the rate law.
Okay.
Yeah,
okay,
so
that makes sense. Thank you.
Oh yeah, no problem. And that's pretty much like everything on rate for this chapter. We just covered all of it pretty much. Let's see if there's something down here that's useful. Okay, as temperature is increased in an exothermic gaseous reaction, all the following increase except.
Your rate constant stays a constant.
Okay. Yeah,
Well,
rate. Yeah, go
that
ahead.
doesn't seem right. No.
Well, it's a
Uh,
constant. It stays a constant, which means it doesn't increase, right?
yeah.
Um.
Oh wait, all of the following increase except yeah, so it's B then.
Well, yeah. So that's annoying. Because there is an equation for rate constant, and it actually does include temperature in that equation. But sorry about
Okay.
that. That's just an. And when I said that's annoying, I meant that's annoying on the part of whoever wrote the question, because
Okay.
I don't know that you're even responsible for knowing that equation.
Okay.
I'm looking really quick while you think about the question to see if you actually need to know that equation.
Oh, well, C then.
Yes, C is the correct answer. Yeah.
Yeah, that actually makes more sense there. I mean, I would argue B or C, but I don't
Yes,
know if I
you do need to know the equation I was talking about. So
Okay, what is the
that yeah, the equation is K is equal to A, which is some constant, times E, like the E from logs, from natural log, raised to the power of negative activation energy divided by RT. And so that's just
Oh, it's the
unfortunately like,
Arrhenius equation.
yeah.
Okay. Yeah, okay, so then I forgot all about that equation. Okay, yeah, then it's C's the one that doesn't increase.
Right. Yeah, because that little T there in the exponent.
Okay.
Yeah, I've never seen that equation like absolutely have to be known. But it gives you the answer on this, or helps you out on this this question. So, and all of these questions are taken from a book called Exam Crackers, which I think I put in your folder, so you can look at any of these questions. I don't think the textbook for this is great, but it has some amazing questions in it. So that's why I use these questions, and the questions are harder than they need. They're like a little harder than the discrete questions on the MCAT.
Mm.
But that makes them great practice questions, because if they're harder than the real thing, then that's useful, in my opinion. All right, and the rest of the stuff is all on half-life, which you don't need to know right now. We'll cover it later, but there's no point in belaboring it if you haven't covered it yet.
Okay,
So
cool.
yeah, we can be done with those questions specifically.
Um,
All right. Any other questions that have come up as we've been discussing through this stuff?
Not really.
I'm trying to think of anything that pops up for me. Here's a good vignette on gases, since the gas phase was part of this, and it's like the only thing we haven't talked about yet. All right, so this is a vignette from Kaplan as well. This is talking about nitrous oxide gas, which is, what is that? Weird. Okay. Nitrous oxide gas is N2O, or wait, NO2, I think. I'm Googling it. I think it's NO2. Nitrous oxide. And this is the laughing gas they give you at the dentist. Oh no, I was wrong. It's N2O. I'm glad I looked. All right, so N2O. So this gas has got some issues surrounding its storage specifically. Why? So what first question is, what is the molecular structure of this thing? What's the Lewis structure of this of this N2O thing? What would it look like?
You have an O in the middle,
Okay.
and then uh I think is it double? I think it's two double bonds. Isn't that correct? Or is it one double bond and
So
one
4
triple
bonds on oxygen would be really problematic. And so let me just help you out really quick. There is not an O in the middle. The O is on one of the sides. So you
bond?
got
Okay.
so your connectivity is going to look like this. So you're connected in this way. So now you just basically have to balance charges, right?
Yeah.
So you can have a Lewis structure where you've got it just set up like this.
Yeah, but
Yeah, there's definitely some issues with that, right? You've got like a positively charged nitrogen, negatively charged oxygen. That's kind of a shitty one. This is better. This is here, at least you've got your positive nitrogen here and that negative charge there. You can also set up the one that looks like this. And this one's not bad as well. I mean, this one has negative charge here and positive charge here, but so it's going to be some combination of those two, pretty much. Anyway, that's nitrous oxide. So how is that problematic when it comes to the PV equals an RT equation?
Pressure times volume is equal to N is the number of moles. Then T is temperature, and then R is the constant.
Right. So whenever you store this gas, there's something about this specific structure of it and the nature that this structure confers onto the molecule, how it behaves, that makes it impossible to use PV equals an RT to calculate the concentration you're giving to a patient. Why is that? Why does the structure of this molecule make PV equals an RT not really work?
Is it because it has resonance forms?
Not because it has resonance forms, but because this equation is the ideal gas law.
Yeah.
And so it predicts the behaviors of ideal gases. So what's an ideal gas?
I actually don't know the definition to that.
Okay. Yeah, so ideal gases are gases that are really like, it's like gases that are pretty much like agnostic to everything else in their environment, including like the walls of their container and the other particles of gas present and stuff like that. So there are a few assumptions that the ideal gas law relies upon, and the further a gas deviates from these assumptions, the less able this equation is to predict the behavior of that gas.
Okay.
All right. So some of these assumptions are, first of all, and so there is no ideal gas. It doesn't exist in real life. But these assumptions allow us to make this simple equation versus like a really complex equation that we would have to use for real gases. Okay. So some of the assumptions are, well, first of all, you've got the assumption that the gas particles don't interact with either each other or the walls of the container. I'm going to go ahead and just put these here. Particles don't interact with each other or walls of the container. And so that assumption is telling us that like these particles probably aren't charged, right? Because if they're charged, then they're going to interact with each other. Does that make sense? You see what I'm saying? Like if they're charged, they're going to either repel or attract each other. Okay. Another one of these assumptions.
Okay. Isn't one of them like that all the collisions are perfectly elastic?
Yeah, that is another one. What does that mean?
That like the energy is perfectly transferred between them.
Yeah.
So like no work. Yeah.
Right.
No work.
Yeah. Right. Okay. Another one is that the particles, I'll just write individual particles take
or spheres.
Zero space. So, or they're like individual particles are infinitely small. Meaning that like the actual space the particle itself takes up is negligible. Okay. Which is even more like not interacting with each other stuff.
Yeah.
Okay. And those, like, just that right there, I think there are 5 total assumptions, but they kind of overlap a bunch and they get sort of messy. What we have right here is pretty good. Like that's pretty much it. You could also say that like the particles don't react with one another, but again, or that they're perfectly inert, but that kind of goes to the same thing.
Yeah.
Okay. And so I'm trying to think if there's anything that I missed. Whatever. And these are all written in the book as well. I just wanted to emphasize some of those. So because this thing is really charged and it's kind of big, it's got 3 molecules on it, or three atoms in the molecule. It takes up a shitload of space versus something that was just like 1 atom in the molecule. is going to take up far less space. So what's the most ideal gas we know of, like in real life?
Helium.
Perfect. Yeah, exactly. Why not hydrogen?
I don't know, actually. I just know
Okay.
heliums.
So atomic hydrogen is extremely combustible. It's like super duper reactive. And so hydrogen only really exists as H2. There is no
Oh,
H1.
yeah,
Okay.
okay.
But then even then though, H2 is smaller than helium from a mass perspective because H2 has an atomic or has a molecular mass of just 2.
Yeah.
Right? Because hydrogen has no neutrons in it, whereas helium has 2 neutrons. So the atomic mass of helium is 4. The atomic mass of H2 is just 2. So why is helium better? You're right, it is better, but why? From that perspective. And I can also tell you this is kind of a hard question. So the reason that it's better is because when you think about the actual size of a molecule, turns out that like the space between the nuclei of individual atoms in a molecule is vast. And so the fact that there are 2 different atoms present in the H2 molecule makes its volume like many orders of magnitude greater than the volume of helium because there's just one atomic nucleus there. So H2,
Okay.
even though its atomic mass is far smaller, it takes up a much greater amount of space.
Okay.
Yeah. So that's why helium's better.
Okay.
Okay, so back to nitrous oxide. So nitrous oxide is, they store it in this like pressurized container, and then you hook up a tube, and then give it to the patient, and the patient breathes it, and they get all loopy, and then you can pull their teeth out. The dentists use this all the time. But if you can't calculate because if you can't use the PV equals an RT equation, then you can't really be sure how much you're giving the patient, right? Because you can't be sure like what volume of gas, how much gas there is in a given volume of a pressurized container versus what it'll change into when you expose it to the atmosphere. So how are we able to give this stuff to people safely? Like how are we able to know how much is in there if we can't use this equation?
I don't know.
Yeah, it's really complicated. So it turns out that when we store this stuff, we store it at extremely low temperature, extremely cold temperatures, and extremely high pressure. Okay. A couple more assumptions. Now I'm remembering the assumptions that I forgot to write down. Sorry. So the individual particle is infinitely small, but then also you have to assume perfectly random motion, right? So meaning that there's likely a large sample of this stuff and very, very in low pressure. So it turns out that random motion, the probability of having perfectly random motion decreases as temperature decreases because total kinetic energy of the particles would decrease. And so you just have less randomness. Like you could have greater probability of all the particles like bunching up in one part of the container, for instance. And also at low pressure, it's just less likely that the particles are going to interact with each other.
Okay.
So then why the hell would storing this stuff store at super low temp and high pressure? Why does that solve the problem? Because that does solve the problem, but why? How's that able to solve the problem? It seems like that would make the problem worse, right?
Let's see. Let's think. I don't know. I actually can't come up with anything.
Right. Yeah. And I didn't get this either the first time I saw it. Nobody gets this the first time. But it's important because this could be an MCAT question.
Okay.
So the reason is because whenever you take this gas and you you dramatically decrease the temperature and dramatically increase the pressure, you turn it into a liquid.
Oh.
And so when it's a liquid, we don't give a shit whether it follows the ideal gas law or not anymore because it's a liquid. So then you
Yeah.
can just calculate how much there is there by just weighing it. You can just calculate the density of it. Be like,
Yeah,
okay, I know I
okay.
have exactly this many moles of it present. So by storing it at high temp, low pressure, or at high pressure, low temperature, we just solve the problem of deviation from ideal gas behavior by turning it into not a gas anymore. We make it a liquid.
Earlier, didn't we say liquids are gases? Or
No,
gases are liquids?
we said that liquids and gases are both fluids.
Fluids. Okay. Can't
Yeah,
get that
yeah.
terminology mixed up.
Yeah, that's really kind of annoying terminology, but yeah, because for something to be a fluid, it just has to have free movement of the particles across one another. So the only thing
Okay.
that isn't fluid is solid,
Okay.
because the particles have to take on this rigid crystalline structure for a solid to form.
Okay.
Yeah, but does that make
Yeah, it
sense? Like you
does.
just increase
Yeah.
pressure and decrease temperature and turn it into a liquid, and now you don't have a problem anymore.
Okay. That makes so much sense. And then you can just you know how much you're giving the patient then.
Right. Yeah, exactly. You know exactly how much you're giving them at that point. So yeah. Cool. So
Okay, cool.
yeah, that's it's such a simple answer and nobody gets that. So yeah. So just be aware that to think about every possibility. It's just like that's just like a probably the biggest benefit of this question here is just like making you opening up the idea that you really do need to consider everything, that everything's fair game and that you can get creative with your problem solving because that's likely to get you the right answer.
Okay.
Yeah, but anyway, so any other questions on any of that stuff?
Not that I can think of.
Okay, cool. I can let you go then because I know we've been going at this for 2 hours now, and I know you've been awake for 30 or so. Yeah.
You know, I'm not too mad at how I did. The thermo and fluid stuff was a little
Yeah, that stuff is complicated for sure.
but I think I did a little better towards the end, or at least being attentive at the end.
Yeah, no, I think you did a really great job today, honestly. Like the thermodynamics and fluid stuff is difficult. The next time the thermodynamic stuff and fluid stuff, so this has just been my experience working with people that the thermodynamics stuff, people tend to get so much better on their second pass through. And the fluid
Okay.
stuff is normally the third pass. Is when people start to really like have it click with the fluid stuff. You just have to do a lot of practice problems on the fluid stuff because it's very counterintuitive.
Okay.
So, yeah, we'll get there. Don't worry about it.
Okay.
You just need to get through the stuff right now. That's because I'm gonna start giving you more reading in between sessions as well. And so keep in mind, like you don't need to know it perfectly. What you showed up with knowing today was amazing. Like that was great. You did an awesome job today. So just keep that up as best you can. And if you don't finish the reading in between sessions or whatever, that's okay. Like
Okay.
I don't expect you to always get it done. I'm just going to try to assign you a bunch or I'm going to try to recommend a bunch. That way, if you shoot for 10 chapters and you get 8, that's better than just like comfortably getting 6.
Yeah, okay.
Yeah. So because it really like this first pass through everything, more than prep for the MCAT, this first pass is prep for the second pass. And
Okay.
yeah. So the sooner we get to that, the better.
Okay. Alrighty. Thank you so much for the session today.
Oh yeah, no problem. I thank you for showing up like prepped and ready to go on this. You did extremely well. So, okay. So for next time, are you wanting to meet on Thursday?
Yeah, Thursday.
Okay, cool. So for Thursday, this is what I would recommend doing this stuff right here, and I'll drop the thing in your folder also. But it'll be physics 5 through 6, what physics 5 and 6, and Gen Chem 9 and 10. Do the Gen Chem reading first. That's way more
Okay.
important. And if you can't do the physics, that's okay. Like the Gen Chem is plenty because that stuff is like probably so you've only got 4 chapters left in the Gen Chem book. And 9, 10, and 12 are the most important chapters in probably the whole book. I would say definitely the whole book, and 12 is the most important chapter in the entire stack of books. So
Okay.
yeah, so what we're trying to do here is get through that chapter 12 as quickly as possible, because that way you can see it more times.
Okay,
So,
cool. Thank you.
oh yeah, no
Alrighty.
problem. So
I'll
yeah,
see
so just
you
do yeah.
Thursday.
So Thursday, what time was it on Thursday? I just want to make sure that we're on the same page. I've got it right here. 4.
Yes.
Yeah. Oh wait, that's the wrong thing. But yeah, 4 on Thursday. Okay.
Okay,
Cool.
yeah. That works.
All right. Cool. All right. Sounds great. I will talk to you then.
Okay, alrighty. Thank you.
Yeah. No problem. Talk to you soon.